Okay, so All right, so our class today is elasticity. And under this topic, we are going to be considering the definition, some properties of metals, Hooke's law, types of elasticity which are classified as modulus, elasticity of modulus of rigidity, and modulus of bulk or bulk modulus. And we'll also consider energy stored in the strain, and we'll consider the relationship between the three moduli, which is Young, bulk, and shear modulus, and the Poisson ratio. So for an introduction, when an external force is applied to a solid, it produces a change in shape, size, or volume of the solid. Now, this change in shape produced on the solid is known as deformation. When we apply a force to an object, it may be an elastic material, whatever material it may be, a deformation will set in due to a change in volume of the material, or change in length of the material, or change in shape of the material. This change in shape is known as deformation. Deformation could be temporal, it could be permanent. Temporal in the sense that when the force applied on the object is removed and the object returns to its original shape and size, that is known as temporal deformation, and it's also called elasticity. That is, temporal deformation is also known as elasticity because when the force applied to cause the deformation is removed, the object returns to its original shape and size. Now, if in the other case the force is removed and the object remains permanently deformed, that is referred to as plasticity. Plasticity. If the object remains permanently deformed, it is referred to as plasticity. That is permanent deformation. For plastic deformation, we have two types, which are dislocation and fracture. Dislocation and fracture. So we'll go on to definition. The first one is deformation. Deformation, it is the change in shape and size of a material produced as a result of application of an external force on the material. Change in shape and size of a material produced as a result of application of external force on that material, that is known as deformation. And then we also define elasticity as the ability of a material to regain its original shape and size after the removal of the deforming force. Elasticity as the ability of the material to regain its original shape and size after removal of the deforming force. While plasticity is when a material remains permanently deformed, even when the deforming force is removed or has been removed, the material remains permanently deformed. Some properties of metal. Here we have hardness, which is a property of a metal that makes the metal to resist cutting action or penetration action. We have brittleness, the property of a metal that allows the material to be bent a little or to be deformed. Then we have malleability, property of the material that allows it to be hammered or rolled to shape. So it's this property that makes material to be designed in different shapes. That is malleability. We have ductility, the property of a material that or metal that allows or permits it to be permanently bent. In such case, you cannot return the material to its original shape. If you try to do that, the material will be destroyed. So it is permanently bent. Then we have elasticity. This is the property of a material that enables it to return to its original shape. We have density, mass per unit volume of a material. We have fusibility, the ability of the material to become liquid by application of heat. This process is often applied in recycle industry, where they recycle used materials like plastic, aluminum, or any other material where they recycle. You see them subjecting the material to a very high heat. It depends on the material anyway. If it's plastic, the heat will not be as much as if it is a metal or aluminum. So the material is transformed to a liquid, and by that they can redesign that material to whatever shape that they want. Then conductivity, property of a material that enables it to conduct heat and electricity easily. Most often we find this property more prominent with metal or conductors. And semiconductors are also another class of material that can conduct electricity to an extent at a particular condition. That is when the temperature of the material is about room temperature. It behaves like a conductor, but if it's below room temperature or 0 point, it behaves like an insulator. So these are some properties of metals or materials. We move on to an elastic spring, typical example of elasticity. So a spring is an example of an elastic body that can be deformed by pressing. So there you see a diagram of a spring. When a load is added to that spring, what happens to the spring? The spring will extend. The spring will extend, and when the load is removed, the spring returns back to its original size. Now, the force by which the spring is returning is called restoring force. Restoring force. You see the question there, F is equal to minus Kx. The negative there is telling us that the object is returning back against the force that pressed it. That is the restoring force. The restoring force is opposite to the applied force, the direction of the restoring force. The force that restores or returns the object back to its original shape and size is in opposite direction to the force applied to press the spring. And that is why we have a negative sign there. So that will lead us to Hooke's law. Hooke's law states that provided the elastic limit is not exceeded, the force applied on the material is directly proportional to the change in length or the extension. So in the previous slide, we had a spring loaded with mass. If we keep loading that mass, that spring with mass, you discover that the spring will continue to stretch, extend. Now, if we keep loading it at a point when the spring gets to pass its elastic limit, the spring will stretch and will not return back to its original size even when we remove the mass. So at that point, we say that it has passed the elastic limit. So Hooke's law is telling us that if that elastic limit has not been exceeded, all materials have elastic limit. If that elastic limit or proportional limit has not been exceeded, the material will always return back to its original shape and size. But once you exceed that limit, the material will not return back to its original shape and size. Say, for instance, your clothes, if you pull it with a force, to an extent it can bear, nothing will happen to the clothes. But if the force applied on the clothes is more than what it can bear, the clothes will tear. The clothes will tear, and that simply means that it has gone, the force you applied is more than what the clothes can bear. So all materials have their elastic limit. So the equation that can be used for that expression, that statement is what we have there, F is equal to minus Kx, where F is the force applied, K is the spring constant, it's a measure of the elasticity of the spring, and X is the extension or the increase in length. So here we have a graph representing force and extension. If we go back to this slide here, we have force is equal to Kx. Force is directly proportional to extension. So if I plot a graph of force against X, my slope will be K. Force against X, my slope will be K. So here we have the graph of force against X, which is the elongation, the extension. So the graph you see there is typical of how a spring or an elastic material will behave. We have the elastic region and we also have the plastic region. So within the elastic region, we have the proportionality limit and we have the elastic limit. The proportionality limit, there you will see that the line is still straight, it's still linear. But at the elastic limit point, at the elastic limit, you see that the line is no longer straight, it's a bit curved. However, in as much as we are still within that elastic region, when the attached load, applied load or force is removed, the material will return back to its original state. So after the elastic limit, we move to plastic limit. That is, when we get to the plastic limit, we move into permanent deformation region. The elastic region is temporary deformation region. The plastic region is permanent deformation region. So at that point, we have permanent deformation. The material can never return back to its original state. And at that point, little force that is applied will cause more elongation. Little force applied will cause more elongation. And it goes on to the breaking point. So at the breaking point, that is where you have the ultimate strength. The maximum strength that the material can withstand without breaking or rupturing, without fracturing. The maximum point a material can stand without rupturing or breaking or fracturing. That is the breaking point. After that breaking point, any little force applied will cause the material to break, to be damaged completely. So this is another graph of another graph we can use to explain Hooke's law. So here we have a graph of stress against strain. And just like the previous graph, we have the elastic region and the plastic region. The explanation is still the same. So here, the proportionality limit, the elastic limit, we have the yield point. The yield point is the point at which the material starts to deform plastically. That is, immediately you pass the elastic limit. The next point is the yield point. It's just like a thin line that separates elastic limit and a yield point. The elastic limit is the maximum strength and a material can withstand without permanently deformed. While the yield point is the beginning of permanent deformation. The elastic limit is the maximum point of elastic deformation, while the yield point is the beginning of permanent deformation. And then we have the ultimate stress point, and then the fracture or breaking point. So stress. What is stress? Stress is force per unit area. When you apply force to a particular area, it is called stress. When you apply force to a particular area, what you have done is you have introduced stress. Stress is synonymous to pressure, and that is why the unit of stress and pressure are the same. The unit of pressure is Pascal, Newton over meter square. The unit of stress is the same, Pascal, Newton over meter square. So force over area is stress, and then strain. We have strain defined here for us as change in length over original length. We can also say extension over the original length. Extension over the original length. Now, types of stress. We have tensile stress and we have compressive stress. Tensile stress, when you apply equal and opposite force on a material, equal and opposite force on a material, that is tensile stress. If you look at that diagram, you see the arrows moving apart. It's just like when you hold a rubber band with your two hands and you pull it apart. You are stretching it, you are pulling it apart. That is, you are applying tensile stress to it. And when you are bringing them together, equal and opposite forces, heading at the same direction, coming together, that is compressive stress. We have an example here. A steel wire 10 meters long and 2 millimeters in diameter is attached to a ceiling, and a 200 Newton weight is attached to the end. What is the applied stress? So we look at this question. You have the length of the wire, you have the diameter of the wire, you have the applied force. You are asked to find stress. Remember that stress is force over area. So we have force there, but we don't have area. However, we have a clue to getting our area. The wire has a circular cross-sectional area, so which implies that the area of the wire is circular, which is pi r squared. Pi r squared. And since the diameter is given, you can get our radius from the diameter using diameter radius relationship. D is equal to 2r, and r will be d over 2. So if we find the area using that expression, pi d squared over 4, substitute in the value of d, which is the diameter. However, diameter is given to us in millimeter. The length of the wire is in meter, which is fundamental unit, and the force is given to us in fundamental unit as well, or derived unit as well. So we have to convert the millimeter to a standard unit, so that is to meter, and that is 2 times 10 raised to minus 3 meters. So if we substitute that, we discover that our area will be 3.14 times 10 raised to minus 6 meters squared. Our force is 200. So 200 divided by 3.14 times 10 raised to minus 6 meters squared will give us the value of stress as 6.37 times 10 raised to 7 Pascal. Now, the example continues. If that wire are carrying a load of 200 Newton, stretches 3.08 millimeter, what is the longitudinal strain? What is the longitudinal strain? This time we are asked to find strain. And strain is extension over original length. Change in length over original length. From the question, our extension is 3.08 millimeter, which if is converted to standard unit to be 3.08 times 10 raised to minus 3 meters. The original length is 10. The extension is 3.08 times 10 raised to minus 3 meters. So 3.08 times 10 raised to minus 3 divided by 10 will give us 3.08 times 10 raised to minus 4. So our strain is 3.08 times 10 raised to minus 4. I've explained this before. Elastic limit. The elastic limit is the maximum stress the body can experience without becoming permanently deformed. If the stress exceeds the elastic limit, the final length will be longer than the original. So an ultimate strength, the maximum strength a body can withstand without breaking or rupturing. The maximum strength of an object without breaking, the maximum strength a body can withstand without breaking or getting ruptured. So if you look at that diagram, you'll see there are 4 of them. The first one, just the wire hanging on the, let's say, ceiling. And then the second one, a load is added, which extended. And then the third one, the load is doubled. The load is doubled. And yet, the wire could still withstand that load. But if that load is increased further, the wire breaks. So the maximum strength, the point of the maximum strength using this diagram is that third one. In the third one, we have the wire having its maximum, that is ultimate strength. After that point, the wire breaks. The wire breaks, which means that we have exceeded the ultimate strength of the material. So example 2, the elastic limit for steel is 2.48 times 10 raised to 8 Pascal. What is the maximum weight that can be supported without exceeding the elastic limit? So if you understand this question very well, you see that the elastic limit is given in Pascal. The elastic limit is given in Pascal, which represents stress. And remember the definition of elastic limit. The maximum stress a body can bear without being permanently deformed. Maximum stress. So if you are given an elastic limit value, it's also referred to as stress value. And the unit also there can guide you to know that this is stress. So we are asked, what is the maximum weight that can be supported? Maximum weight, which is the force that can be supported. Force that can be supported. Maximum weight. F. Stress is force over area. Stress is force over area. Stress is given. You are asked to find F, force, and then area from our previous example, area is 3.14 times 10 raised to minus 6 meters squared. So if we make F, which is force, the subject of the equation, to be stress times area. So stress 2.48 times 10 raised to 8 times the area, which is 3.14 times 10 raised to minus 6. That will give us 779 Newton. 779 Newton. That is the maximum weight that the wire can withstand, or the steel can withstand, without moving into plastic region, without being permanently deformed. And the example continues. This time we are asked to find the weight, maximum weight again, given the ultimate strength. Remember, ultimate strength is also defined as the maximum stress. And if you look at the unit as well, the unit is Pascal. The unit is Pascal. And the definition says maximum stress a body can bear without rupturing. So that is a stress value that is given. And then we are asked to find the maximum weight, which is force. So stress is equal to force over area again. We are asked to find F. A is known, S, stress is known. So cross multiply, stress times area will give us the force. And that is 1536. 1536 Newton. Now, types of elasticity. There are three types of elasticity. We have the linear elasticity, called the Young modulus, corresponding to linear strain. We have elasticity of tape, or shear modulus, or modulus of rigidity, corresponding to shear strain. And we also have elasticity of volume, or bulk modulus, corresponding to volume strain. Now, what is strain? Strain is the effect of stress, the consequence of the stress, When you apply stress to an object, to an extent, the object becomes strained. It's just like you, maybe during the day you have been seriously working, maybe at home, washing clothes, cleaning the house, cleaning up the cobwebs, and so many things. You've been doing that from morning till, let's say 12 noon. And then you feel that you are stressed up. When you are stressed up, what does that mean? You are tired. So when you are stressed up, the aftermath of that is becoming tired. So that is how stress is to strain. When an object is stressed, it becomes strained. So modulus of elasticity. Young modulus, also known as the modulus of elasticity, is a material property that describes the stiffness of material under tensile or compressive stress. Tensile or compressive stress. It is named after the British scientist Thomas Young, who first introduced the concept of Young modulus during its research work on the material. Now, Young modulus is denoted by E, and sometimes you see it denoted by a Y, capital Y, or E. So you can use capital Y or capital E to denote Young modulus. It is the ratio of stress to strain. So Young modulus is stress, simply stress over strain. Stress over strain. The unit is Pascal. Since strain does not have units because strain is change in length over original length. Change in length over original length is strain. So the unit cancels out. Strain is dimensionless. It does not have units. And now Young modulus is stress over strain. The unit of stress is Pascal, which makes Young modulus to attain the unit of stress. So the unit of Young modulus is the same as the unit of stress, Pascal or Newton per meter square. So when the deforming force is applied to the body, only along a particular direction, the change per unit length in that direction is called longitudinal or linear or elongation strain. Like I said before, the effect of stress or the consequence of stress on a body is strain. You apply a force to a particular part of a body, force over area, force applied to an area and a particular part of the body gives us stress. So that stress will culminate to strain. That stress will culminate to strain. So the force applied per unit area of a cross section is called longitudinal or linear stress. Now, the ratio of the longitudinal stress to linear stress within the elastic limit, So Young modulus also applies within the elastic limit. Within the elastic limit is called Young modulus. Capital E or Y denoted. So if we put everything we have said together in equation form, stress over strain. Stress is force over area. Strain is change in length over original length. So if we put all together, we have Young modulus to be force times original length divided by the area times the extension. So FL over A change in length. The change in length sometimes in some textbook people you can see it as small letter E, which is standing for extension, or X, capital small letter X, standing in for displacement. So when you come across small letter E in an expression that has to do with Hooke's law or letter X, still know that it means the same thing as delta L, that is extension or change in length. So here we have an example. In our previous example, the stress applied to the steel wire was 6.37 times 10 raised to 7 Pascal. And the strain was 3.08 times 10 raised to minus 4. Find the modulus of elasticity for steel. So here we are asked to find modulus of elasticity or Young modulus. We have calculated strain before, and we have calculated stress before in our previous 2-3 examples. So now the question continues, and we are asked to find Young modulus. So Young modulus is stress over strain. Young modulus is stress over strain. So we substitute the value. When we substitute the value, that is 6.37 times 10 raised to 7 Pascal over 3.08 times 10 raised to minus 4. Our modulus will be 207 times 10 raised to 9 Pascal. 9 Pascal. 9 Pascal. Here is another example. We have Young modulus given to us for Young modulus for brass is given to us as 8.96 times 10 raised to 11 Pascal, and then a weight of 120 Newton is attached to a wire of length 8 meters. We are asked to find the increase in length given the diameter of the wire as 1.5 millimeters. Increase in length, which is the same as extension or change in length. So we have the Young modulus, we have force, we have original length, we have diameter, we are asked to find extension. Now, for this, Young modulus is equal to stress over strain. Stress is force over area. We have force, but we don't have area, which means we have to find area using the diameter given to us. Remember that the wire is assumed to have a circular cross-sectional area, which means that the area is pi r squared. So we are given a diameter for that material. If we substitute that to the area formula pi r squared, we have what you see there, pi d squared over 4. So our area is 1.77 times 10 raised to minus 6 meters squared. Now we have area, we have force, so that area and force will give us stress. Then we have original length. We are asked to find change in length. Remember, change in length of original length will give us strain. So we are asked to find extension, that is change in length. So putting all together in that expression, we make change in length the subject of the formula, which should be force times length over Young modulus times area. Force times length over Young modulus times area. So if we substitute in those values, we have our change in length or extension or increase in length as 0.605. 0.605. So we are going to end the class here today. By Friday, hopefully, we'll meet again for another 1 hour class to conclude the rest of this topic, which has to do with shear modulus and some calculations under shear modulus, bulk modulus, and then we'll also look at the relationship between the moduli and then Poisson ratio, as well as energy stored in a material. So have a wonderful day. Thank you.